Okay, in a Poisson regression, one of the things we have to look out for is overdispersion or underdispersion. Overdispersion is, to recap, is when the variance, the conditional variance, is greater than the conditional mean, which violates the condition in Poisson regression that the mean is equal to the variance. And underdispersion is the opposite. The conditional variance is less than the conditional mean. If we don't, if the mean variance relationship doesn't hold, I mean doesn't equal to the variance, then Poisson MLE is going to be consistent, but standard errors are wrong, hence the RT statistics are wrong. We got around that by using Poisson QMLE, quasi-MLE, which is robust to that mean variance relationship. Another way to deal with over under of a mean variance relationship not holding is the negative binomial MLE. This negative binomial MLE is a contender if you have overdispersion but not underdispersion. Okay, so we're going to look in the two cases. We're just going to run examples. Case of overdispersion. Result is that estimates of both Poisson QMLE, negative binomial MLE are consistent. Remember, consistency is a large sample property. That the parameter estimates basically equal, very vaguely equal to the true value. But this negative binomial is more efficient, i.e. Has a small variance in the class of all consistent estimators, if the NB assumption holds. And the NB assumption puts a structure on the dispersion parameter, sigma square. Okay, we're not going to spell out what that assumption, the actual form is, but intuitively why it'd be more efficient if it holds is because then if you're using more information and that information is correct, then you're going to gain something compared to the Poisson QMLE, which doesn't have any kind of put any restrictions on that mean variance relationship. So for the overdispersion example, we looked at the biostatistics example, we looked at the number of infected cells on a microscope slide. So if we run that again, this is what we have. And there's a dispersion parameter here, it's bigger than 1. Alright, this is dispersion parameter is not the one that I showed you how to calculate in a previous video. I don't know how this is exactly calculated. Anyway, the fact is it's bigger than 1. So suggest there's overdispersion. I want to compare the results of the estimates and the standard errors if I also now run negative binomial MLE. To do that, I have to load the mass package, and then the command is glm.nb. Like this. Okay, at the end we can put in a link function, a log link. Right, now if I look at this, here you go. What we want to do is compare the estimates and the standard errors. Now for the estimates we can use something we did before, and that's basically extract the coefficients and then group them together next to each other. Like this. Okay, you can see that the estimates of the Poisson QMLE exactly identical to the negative binomial MLE estimates. Okay, that's good, no difference there. How about the standard errors? Okay, because I can't get all this onto do what I did here for the standard errors because of the mass package doesn't allow that. Let's just, not the greatest thing, but let's have a look. Alright, well what you do is just look at these numbers here, and then what you're going to see is that they're similar but not exact. Okay, here are the standard errors for the NB. Here are the standard errors for the Poisson, but QMLE. But don't be too concerned about the standard errors. Look more at the t and the corresponding p-value. So what's the result here? Significant, 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 but lesser to extent, not significant for weight over dummy, not significant for the final interaction. Does it match what we get here? Yes. The only difference is that, real difference is that the second dummy here is significant to 0.001 significance level. This is significant to only 1%. How similar the standard errors will be will depend on the degree of overdispersion then. So if there is no overdispersion, you'd expect those two results. They're both very, very similar. If the dispersion parameter is big, some people say they opt for the Poisson QMLE because it's more of its robustness property, so it doesn't actually place a condition on the relationship between the mean and variance. Next, let's look at the case of the underdispersion. Okay, for underdispersion, Poisson QMLE is robust. Okay, it's robust over underdispersion. This negative binomial MLE is not robust, so it's going to be inconsistent in the case that we have underdispersion. So the estimates, we expect them to be different. Okay, something else I want you to note, that the rule of thumb to spot over an underdispersion, that the residual deviance divided by its corresponding degree of freedom is much bigger than 1 implies overdispersion, is a bit vague. What do you mean by much bigger than 1? So I say it's better to run both MLE and QMLE and look for the dispersion parameter. Right, for this example I've got fertility data. The dependent variable is the number of children in a family. So it's what I'm going to do. I'm going to run first the Poisson one. Then I'll run the quasi-QMLE for Poisson QMLE, and then to look for the dispersion parameter. Dispersion parameter is less than 1. Now, empirical studies usually find that the dispersion parameter is greater than 1, but here we've got an example, it's less than 1, but not too much less than 1, about 10% lower. Now I'm going to run the negative binomial, same again. I'm going to save the coefficients from that regression, call it into an object, and then I save the coefficients from the previous two regressions as well. Now I'm going to compare all these coefficients. Okay, so here you go. So C1, that's Poisson, that's Poisson QMLE, and this is negative binomial. So obviously these two are exactly the same. These guys are the same. Well, the degree of underdispersion isn't extreme, but you can see that there are differences here. You'd expect that the bigger the underdispersion, the bigger the differences of the estimates here, because we know that from theory that Poisson QMLE is going to be consistent, whereas this guy, the negative binomial, is not going to be consistent. So they're the differences. On the whole, it seems like that if we're interested in estimating parameters of the conditional mean model, that there's more going for Poisson QMLE because it's robust to the mean variance relationship. The negative binomial model implies that there's going to be overdispersion, not underdispersion. So it's ever going to work well if there's overdispersion. But it also puts another structure on the mean variance relationship. And if that structure holds, then it's going to be more efficient than Poisson QMLE, otherwise it isn't. And if you read around a bit, this talk of there's more than one type of condition on the mean variance relationship. There's what they call a neg-bin1 model and a neg-bin2 model. In a neg-bin1 model, the dispersion parameter over dispersion parameter is fixed, but in a neg-bin2 parameter, neg-bin2 model, sorry, the dispersion is allowed to increase with change in the conditional mean. Okay, so that's it.